Hi, welcome to Module 6, where we're going to continue with our discussion of classification problems in machine learning. So we're going to pick up where we left off in Module 5, where we estimated a random forest model to predict the number of accessory dwelling units in LA. But here we're going to focus in this lecture on how we interpret our model's success. How do we assess their predictive accuracy? So we really skimmed over that in the last lectures, and so now we're going to dig in. So first of all, let's recreate the same model as we estimated before. As always, follow along with this code, which is in your GitHub repository. So this is exactly what we've seen before. So we import our libraries. We load in this join data frame that we created 2 lectures ago, and save to disk. And we're going to create dummy variables for these use types and use descriptions. We're going to add these dummies to a join data frame. We're going to create a list of the x variables that we want to include in our model. We're going to specify a y variable. And we're going to create a data frame that has a subset of what's in join data frame, just with these x and y variables that we want to keep. We're going to drop the nulls. Then we're going to create our train test split, hold back a quarter of the data for testing. A random state parameter guarantees we're going to get the same result as before. And then we're going to initialize the random forest classifier object. We're going to fit it, and we're going to generate some predictive values. Now let's also re-estimate a more simplified version of the model. And that's because when we assess the predictive performance, it's useful to compare it to. So if we're predicting less than 1% of parcels have ADUs, is that good? Or is it because even though we're short, it's just really hard to do? There's a lot of randomness in the variation. Or can we do better with a different model? So the prediction accuracy is often relative between different modeling approaches. So we've done the same thing as here, but this is just a smaller version of this model, just with these 3 x variables, which we're using to predict. And then the same is what we've done before, you just have a 2 suffix. So last time we predicted that 0.1% of the parcels would have an ADU, or less than 0.1% in the simplified model. Let's just confirm, and we do, that we get the same overall prediction as we did in the last lecture. Okay, so with these raw fractions, this more complex model is doing better, but both of them are still far short of this real fraction. So how do we examine the predictive accuracy? Well, scikit-learn has several useful functions, which we're going to walk through in turn. First of all, the confusion matrix. And this is what I find the most intuitive. This gives the number of observations that fall into each predicted and actual category. For example, do you have a true positive? It was really true in the real world, and your model is predicting it to be true. The accuracy score gives a fraction of accurate predictions. And this is because just a high prediction rate doesn't mean you have a good model. If you want to predict whether any individual is going to be struck by lightning tomorrow, a really accurate model would just say, well, they're not going to be hit by lightning, because almost no one is ever hit by lightning. It's a very rare event. So you could just predict no for everyone. So it's accurate, but it's not very useful. So this fraction of accurate predictions, in some cases, can be useful, but treat it with caution. So the classification report delves into this in more depth. So it looks at the precision and the recall. So precision gives a fraction of true positives compared to the number of predicted positives. Basically, how many of the ones that you're predicting are correct. If you're predicting ADUs on these parcels, how many of these true predictions are right? And then recall is how many of these true positives, the ones that are really ADUs in the real world, what does that look like compared to the number that you're actually correctly predicting? These will make more sense when we look at some examples. So let's do this. So let's look at confusion matrix, and the syntax is pretty simple. We just pass the real values and the predictive values. We can give them labels if we want. So our true values are our holdback sample, right? Our testing portion of a data set. So these are the real values, and then these are our predicted. So what does this look like? So these are true, true, these are false, false. So we're actually correctly predicting that most parcels don't have an ADU on them. But what we're not doing very well is these true falses, right? Where there's a lot of parcels that do have an ADU, but we're not predicting that. So this is real world true, our prediction is false. So you can read more about the documentation for the confusion matrix. We'll come back to the confusion matrix in a moment, but let's look at our accuracy score. It looks really good. Wow, 97% accuracy. But as we just saw, that's being driven by the fact that ADUs are pretty rare. It's easy to get a high accuracy score if you just picked no for every parcel. So what's this classification report? Well, remember our precision. What's our definition of precision up here? This is the fraction of true positives compared to the number of predicted positives. How many of our positive predictions are correct? So that's actually pretty good for our falses, right? So if we're predicting false for a parcel, most of these false predictions are actually correct. And actually most, not quite as good, but actually 74% of our true predictions are correct. And what we're really not doing well is in this recall. So this is if the parcel really has an ADU, how many times are we predicting true? And that's just 3% of those actual ADUs we're getting right. We can also plot the confusion matrix, and this is one of my favorite ways to just quickly look at the predictions. So here we see that 188,000 parcels, they don't have an ADU in real life, and we're predicting that. So this is what we're doing really well. This is true in the real world. 6,000 of these, we're actually predicting false. So this is showing where we're not doing so well, right? Of the 6,200 and so ADUs in the real world, we're only getting 189 of them. But we're not doing too badly up here. We're not predicting many false positives. And we're not predicting true when there really isn't an ADU in the real world. So this confusion matrix display is a pretty quick and simple way to get a visualization for the overall accuracy of the model, both in terms of overall accuracy, but also in terms of these four subcategories. Well, how does this compare to our simplified model? Well, it might not be great, but it's actually doing much better than our simplified model. Right here, we're only getting at 14 of the true positives. Most of these parcels where there is an ADU, we're ending up with false negatives. We're predicting false, but it's really true. So one way to say is a more complex model, well, it's not great, but it's better than a simplified approach. Right? We're getting value by adding in these extra fields. And perhaps this isn't surprising. ADU construction is going to depend on many factors that we don't have data for. What about the shape of the lot? Is it easy to squeeze a backyard unit into a corner of your backyard? Or is your lot a weird shape, or the existing building a weird shape that makes that harder or more expensive? We don't have any data on the owners. Can they afford an ADU? Do their personal circumstances mean that they're motivated to pursue one? For example, an elderly relative who they want to be able to live to close by. A motivation for many people to do this. So perhaps bringing census data, or even better, individual level data on the owners might help us do better. But so in that sense, it's not actually that disastrous, our predictions, when we're only using these really limited set of measures from the assessor's recorders database. Even if our predictions are not always accurate, these predictive probabilities can be informative. And one way to think about them is often to map them. Now we can access the probabilities from this RF object. So this is a little more nuanced, right? Rather than just saying this observation is true or false, we're actually getting something, well, is this a 40% chance of being true? Is this an 80% chance of being true for this parcel? And so we're getting an array here. This first column is a probability that false, so the probability of no ADU on this data set. And this column is a probability of being true. So perhaps even though there's a 4% probability of an ADU on this parcel, if you have 30 or so parcels, then it's pretty good odds that one of these 4% is going to turn out to an ADU in reality. So this is just from our testing data set. Note that we want to actually get the predictive policies of all of them from our testing and our training data set. So let's concatenate these two. We actually create a list of these two and put them together into a pandas data frame. And let's predict the probabilities for all of them. We see that the first three rows, these are the same from a testing data set, but the last three rows are from this training one here. So the first bit is the same as this. The last bit isn't because this is going to be a longer array. Well, this is an NumPy array that RF predict probab is generating. But we can easily turn an array like this into a pandas data frame. So this is exactly what we had before. This is this line of code here. We're just passing it to a pandas data frame constructor. And then we're telling pandas what our column names are going to be, predicted that there's no ADU and predicted that there is an ADU. So this is just a little easier to interpret and to look at. Now let's join our original test data back to these predictions. Well, one wrinkle, we just have an integer index on predictions. Here we have APN on xtest, but here we have an integer index. So fortunately, resetIndex is a pandas function that can change this back to a sequence from 0 to the length of the data frame. And then it's going to put APN back as a regular column. So let's create predictions that has an integer index. Let's look at this. And then we're going to join it, predictions, to our original test data. So what are we doing? We're joining this predictions data frame back to our original characteristics, which have some useful characteristics, particularly the lat long, which we can then use to map where are our predictions taking place in space. So let's map these predictions. So pause the video here and see if you can do it for yourself. In particular, figure out how you can convert this predictions data frame to a geodata frame that includes a geometry column. And we saw how to do this in a previous module. We need to take this lat and long and create a geometry column out of it. So let's see how that goes. Well, let's import our GeoPandas library. Let's create our predictions, let's call it the same name for simplicity, as a geodata frame, which takes our predictions data frame, not geodata frame. The difference is going to be the geometry column, where we use our GeoPandas points from x, y. What's the x? Well, that's going to be the center long column. This is called center long, and this was center lat. Center lat, and then we're going to tell it what the coordinate reference system is, which is our lat long 4326. So we have a geodata frame. Now let's map it. So let's import our libraries, create a blank figure object. Now again, our base map's in Web Mercator, so let's reproject this to Web Mercator 3857. Let's plot. What are we going to plot? Well, let's plot the probability of there being an ADU. And let's do a small marker size, so as a here, and plot it on this axis object, and add a base map. Okay, so we get our map. Okay, well, this isn't very informative, right? We have a lot of markers, but it probably says more about where the parcels are than the presence of an ADU or not. So let's think how we can refine this map. There's a couple of strategies. Well, maybe we don't plot parcels with less than a certain probability of having an ADU. so these very small dots don't just aggregate into a big glob. We could use a different color map. A plot function takes a CMap argument. We could use a smaller marker size to avoid these parcels just overlapping. Or perhaps we could scale the color map so it tops out as a lower value. Here we see, actually we don't have a color bar, but we could adjust the color map scale so that it tops out at a lower value. Let's try this one and this one. So what are we doing here? Well, first of all, we're subsetting the data frame. So we're only taking the data frame where our probability of an ADU is greater than 0.1. So we're using a much smaller data frame to plot. Let's project it. Now let's use color map purples. And then let's make this, we can make this an even smaller marker size if we want. And our Vmax means our color bar is going to top out at 0.2. So anything greater than 0.2 is going to be the same color as 0.2. So if it has an 80% probability of having an ADU, it's going to be the same color as it has a 20% probability. Okay, so this looks a little better, but we're still perhaps showing more about where the parcels are than where the ADUs are. We see a large cluster in the San Fernando Valley. We need to pause the video and experiment with different values for Vmax. See what this parameter does, and if you can get a better map from adjusting that value. And I also want you to experiment with what other color maps you can use. Explore the Matplotlib documentation. So pause the video here and experiment with both of these. So perhaps you had some success with those. I think that perhaps changing the marker size is a better way to go than a color. So let's create a scaled column. We did something similar to this before. That's just 1% of the size of the column that we were plotting before. So this value is just going to be a lot smaller, so our markers are going to be turn out smaller. And our other stuff is the same as we had before. Perhaps this is better, I'm not sure. It's still not clear how we can distinguish areas with lots of parcels from areas that don't have many parcels but have a high propensity to have an ADU. Perhaps you have some ideas. We're going to leave the mapping here, but my inclination would be at this point to aggregate. And perhaps we aggregate to a grid, or perhaps we aggregate to census block groups in order to make this propensity to have an ADU come out a bit more clearly from the map. So the takeaways I'm going to leave you with. These confusion matrices are an excellent way to assess a predictive performance, especially if you have a binary outcome, like true or false. There's some other ways to assess a performance, like the accuracy score, perhaps a recall and precision, but confusion matrices are usually a good first step. And then if you want to dig a little more into the probabilities, so rather than this kind of arbitrary, like is it 0.49 or 0.51, if you get 0.49, you're predicting false. If you get 0.51, you're predicting true. Perhaps you can look at those probabilities in more nuance, and mapping and other descriptive plots are a great way to do that.